Now we're going to talk about some of the other properties besides melting point and boiling point that are impacted by intermolecular forces. So the first one we're going to talk about is viscosity. And viscosity is the resistance of a liquid to flow. So you maybe have experienced this when you work with honey or molasses. Molasses always comes up, even though I'm like, who actually eats molasses? I don't know. But yeah, so very like hard to flow. You kind of think of it as sticky a bit. Even oil you might think of as kind of viscous. It's a little thick. So here we have a certain polymer that has a higher molar mass, a higher chain, and it's going to have a higher viscosity. So even though they both have the same opening compared to this one that has lower viscosity, we're going to have higher IMFs, leading to it pouring a lot slower. It's just having a hard time pouring. So it's has a high viscosity. Viscosity is going to increase as we have our intermolecular forces getting stronger. But just like if you had honey, the way you can get honey to go from being very, thick and viscous and hard to get out to being easily poured is that you increase the temperature. So you can get it warmer. By doing that, you're going to increase the kinetic energy, making the molecules move faster, and therefore they can flow past each other a little easier. So here are some of the measurements. We can see all of these chains are hydrogen carbon chains, so very nonpolar. They're just getting longer and longer, and so you can see that the viscosity is going up, and that's because we have a higher molar mass as we get down there, as well as more surface area. Next thing we're going to talk about is surface tension. We're going to zoom in on this molecular diagram of some water. So we can see here that within the water body, we have, for this molecule here, we have forces, intermolecular forces going in all directions and evening out. When we're at the surface, though, we end up having a net force down. There's nothing above those molecules to cancel out. And so what ends up happening is it makes the top layer hold a little tighter together in order to kind of balance it out. That's what surface tension is. It's the fact that the surface molecules are held tighter than deeper into the liquid body. So it kind of is like for water anyway, it's like it has a skin on top of it due to extra inward forces on the surface. This is why water will bead up, because we end up getting, if we have like a nonpolar surface, there's no attraction for it to go down. Because it's a polar compound, it's not going to have very much attraction to a nonpolar surface, and so we get this beating up, and so the surface tension is around the whole sphere. This is what causes these bugs to be able to walk on water, because they have they're spreading out their body weight over many legs and giving a large surface area. Kind of think about it when you go like snowshoeing, you have a big surface area so you don't fall in. Same thing here with these bugs. They're able to actually have less force than the surface tension, and so they don't break it and they can walk on the water. Along the lines with both viscosity and surface tension is cohesion and adhesion. So cohesion, means together, and ad means to or toward. So cohesion means sticking together. Adhesion means sticking to something else. So IMFs that bind molecules to one another, those are the cohesive forces. Keyword being binding to one another. And then IMFs that bind a substance to a surface are the adhesive forces. We can think about, right, we use adhesives when we are wanting to stick, glue things together, or we're going to tape something to the wall. We use an adhesive. So that's sticking molecules or the forces of molecules to another surface. And these are really important in capillary action. So capillary action is the rise of a liquid up narrow tubes. You maybe have seen this. If you have a cup of water so here's the liquid, and you put a straw into it, if you look very closely, the amount of water goes above the level of the surrounding water. That's due to some adhesive forces on the surface of the straw and cohesive forces within. So, let me zoom out. So both adhesive forces attract the liquid to the wall of the tube, and the cohesive forces keep those molecules attracted to each other. So we can see a really nice, I like this image a lot because we have the molecules, the water molecules cohesively bonding together while also holding onto the surface. This is key that they mentioned that the surface is polar or charged because water is a polar molecule. So for it to feel some adhesive forces to the surface, it needs to have some IMFs that attract it to it. So it needs to be a polar surface. So we can see this here. We have water and mercury in a glass test tube. Key thing you want to know is that glass is made up of silica, which is you can see a bunch of oxygen atoms on the surface here. So oxygen atoms, generally when they're bonded with other atoms, they tend to be polar. And so what we see for the meniscus of water is it has a concave shape, meaning that the water molecules are going to have strong adhesive forces to the glass. They're going to attract to that polar glass and causing the meniscus to point in a concave way. If we look at mercury, mercury is a metal, and so it's going to have metallic bonds. It's more attracted to itself. It has higher cohesive forces, and it doesn't really have an attraction to silica or glass, and so it has no adhesive forces. So basically we get this convex shape where the cohesive forces are really strong internal and the adhesive forces are very weak. So let's zoom out and finish up our last little bit of notes. So water has stronger adhesive forces with the glass, and mercury has stronger cohesive forces with itself. And you can look at that, you can tell by the shape of the meniscus and how those forces are, which force is stronger.